My dear students, now we are going to look at multiplexer. So what is multiplexer? We will look at what is the alternate for the multiplexer, then what exactly its operation, then followed by how to design multiplexer. Okay. So multiplexer is used to select a data from given set of data elements. So let's see that. So in short we call this MUX, or it is also known as selector. Its job is to select. Now this selector will come with our multiplexer. What is multiplexer? You say multiplex. You to watch a movie, you go to multiplex, right? What is multiplex? Multiplex is one where we have shopping mall, number of theaters. What is multiplexing is putting together. Actually, multiplex is putting together. So MUX or multiplexer is in digital circuits. The job is very simple. Let's say I have two inputs, say data I0 and I1. To choose one out of the two, I will be having select line S0. This is input 0, input 1. There will be output Y. Now what is exactly this is going to function is as if there is a switch inside. So if I want to draw this circuit, equivalent circuit, there is I0 and there is an I1. Okay, and there is an output. Okay, this is a switch which is operated by, which is controlled by, S0. When S0 is equal to 0, your Y is connected to I0. When S is equals to 1, when S is 0 is equals to 1, okay, this will be connected to here. So this is for S is equals to S0 is equals to 0. This is the connection established when S0 is equals to 1. So what I can say this is, wow, how can I represent this in the truth table form is this. What is that is, I say that there is an input S0, there is an output Y. When S0 is 0, my output is I0, and when S is 0 is 1, my output is I1. What is I1 here? What is I0? I0 is a binary variable. What is meant by binary variable? Either it can take 1 or 0. What is I1? This is also a binary variable which can take 1 or 0. So the meaning of this is when S0 is 0, when S0 is 0, Y is nothing but I0. That means if I0 is 0, then if I0 is 0, Y is 0. If I0 is 1, then Y is 1. Similarly, what I can do is, what exactly the possibility is, when S0 is 1, S0 is equals to 1. When S0 is 1, what is your output Y? Y is I1. So if, what exactly, if I1 is 0, then Y is 0. If I1 is 1, then Y is 1. This is how it is going to function. So in general, if at all I look for, there will be 2 power n number of inputs and one output. N can be any value from 0 to any value. Infinity I can, but in generally we never go for infinite. We will go for few values, maybe from 0. So n is equals to 0 is not a 2 power 0. 2 power 0 is 1. 1 is to 1. So it is 1 to 1. I don't require any multiplexer. So we never use n is equal to 0. So we will be starting from 1 to infinity. Of course, I can say n is equal to 0 to infinity, but there is no meaning when n is equal to 0. So instead, I can also say that n can vary from 1 to infinity. Okay, I can also extend my statement, or I can stick to this. I can give a condition. So anything is okay, fine. So now 2 n is equals to 1. When n is equals to 1, 2 power 1 is to 1 is 2 is to 1. So the smallest multiplexer possible is 2 is to 1. Okay. For this multiplexer, we have seen how exactly the truth table is. From the truth table, we will further look into how to design this circuit. What is there inside is nothing but the design from the operation. That is possible, of course, that we will see anyhow. Now when n is equals to 2, it is 2 power 2 is to 1. So next is 4 is to 1 multiplexer. Now if I take n is equals to 3, n is equals to 3, if at all I take, then it is 2 power 3 is to 1, which is 8 is to 1. So in general, it is next it will be 16 is to 1 mux, 32 is to 1 mux, 64 is to 1 mux, 64 inputs, 1 output. Okay. Then for any multiplexer, there will be a selection lines. These two are what exactly these two? These two are inputs. This is called selection line. These are input data. Whereas this is selection lines. Selection lines. What is the other name that I told for the multiplexer? Is selector. The appropriate name for the multiplexer or MUX is selector. So to select one out of the possibilities, means you choose 1 out of 2 or 1 out of 4, okay, or 1 out of 8. Okay, how many selection lines required is depends on the value of n. If n is equals to 2, selection lines are 2. So selection lines are n. Number of inputs are 2 power n. Number of outputs are 1. For n is equals to 2, selection lines are 2. For n is equals to 3, selection lines are 3. Selection lines are 3. So I can say in general, it's like this. For a 2 is to 1 multiplexer, there will be 2 inputs. There will be one selection line which is also an input. There is only one output. Okay. So this is nothing but the selection line S0. This is input I0, I1, then Y. In addition to this, there exists a enable input. What is this enable input is En. How it functions is, this is 2 is to 1 multiplexer. How it functions is, when enable equal to 0, okay, your output is always 0, nothing, irrespective of S0, irrespective of I0 and I1. So it is not going to function. When enable is 0, it is not going to function. For what sake we are going to have this enable is to save the power. When I am not working with this, if I make enable is equals to 0, okay, I am going to save the power. If when I am working with this, if I make enable is equals to 1, then it will be enabled. That means it is ready with power supply. Okay. So enable is like a power supply. Okay. So I'm giving the power or I'm not giving the power. When enable is 0, you are not operating with this MUX, then you can save the power. So that is the reason why generally multiplexers are there with enable input. Now next capability, next higher order, I can say for n is equals to, say for 2, there will be 4 inputs. 4 inputs. There is an enable input. Then there are 2 selection lines, 1 output. One is S0, another one is S1. S0 is LSB, S1 is MSB. So I can have a data line I0, I1, I2, I3, then followed by enable. This is 2 power 2 is to 1, which is nothing but 4:1 mux. There is only one output. Okay. Now if you want to look at the truth table, yes, truth table is possible. What is the truth table that I am going to work with here is very simple. I have S0 and I have S1. Let's say enable is there, enable is 1, enable is 1 for all the cases. For 0, 0, 0, 1, 1, 0, 1, 1. For 0, 0, output is Y0. For 0, 1, output is I1. For 1, 0, output is I2. For 1, 1, output is I3. That means either this may be connected to output, or this may be connected to output, or this may be connected to output, or this may be connected to output based on the values of S0 and S1. Okay. So this S0 and S1 chooses one out of the four. Okay. So this is how the 4:1 mux look like. Further, what I can do is, even I can build 8:1 mux. So if you want to have 8:1 mux, there will be 2 power 3:1 multiplexer. As n is equals to 3, there will be 3 selection lines, S0, S1, S2. The number of inputs will be 8. Say I0 to I7, I1, I2, I3, I4, I5, I6. Only one output Y. Okay. So there may be an enable input. Somewhere here I can put it. There can be an enable input EA. So this enable can be active high or active low. If there is no bubble here, it is called active high. If there is a bubble, it is called active low. For this circuit is going to work when enable is equals to 0. Okay. So when there is a bubble, we call it as enable bar. So when enable bar is equal to 0, it is going to work. Okay. If there is no bubble, we call it as enable. So when enable bar is equals to 1, then this circuit is not going to function. This is known as 8:1 mux or 2 power 3:1 mux. Similarly, what I can do is I can go for 16:1 mux. 16:1 mux. Say, how many selection lines? 4 selection lines. S0, S1, S2, S3. How many inputs? How many inputs? How many inputs? Totally 16 inputs. Dash, 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 dash up to I15, starting with I0, 2 power 4:1, 4 selection lines, S0 to S3, only one output. There can be enable input. Enable can be active low or active high. Here I am taking an active high enable input. Okay. So this is what exactly output Y. Now what we try to do is, we will try to design a small multiplexer, which is 2:1 multiplexer design. So from its functionality, I will get a truth table. From the truth table, we will design the circuit. So I want to know what is there inside this box. Okay, that is what exactly the investigation. So I0, I1, S0 is input, output is Y. Say I have an enable input. So enable should be equivalent to 1. S0 is 0, S0 is 1. Output is I0, I1. So can I write this expression as Y is nothing but enable S0 bar I0 plus enable S0 I1. Okay. So this is what exactly the output is. From this, if at all I implement this expression, that itself is multiplexer. Which multiplexer? 2:1 mux. So I take enable. Let's draw the circuit diagram. I have enable. I'll take enable. I have S0, S0, S0 bar inverter, S0 bar. Then I have I0 and I1. So what I try to do is I will take an AND gate, for which S0 is one of the input, enable is one of the input, the other input is I0. This will give you one output. Next, what I try to do is, I'll take enable, then I'll take S0, then I take I1. So for this AND gate, I'll put I1 over here. Then I will OR them together. Okay, this is my Y. So now it is clear. Enable S0, I0, I1 are inputs. Output is Y. Okay. The same thing is shown in this form. That is directly here we are showing whatever I am showing this circuit is there inside. That means to say here it is I0, I1. Here it is also input S0. We are getting output Y. Okay. So this is what exactly this box. I mean to say, let's say AND OR gates are going to implement this 2:1 MUX. Okay, this is what exactly 2:1 MUX design. Similarly, one can design any multiplexer, maybe 4:1, maybe 8:1, maybe 16:1, maybe 32:1, maybe 64:1, maybe 128:1, or maybe 256:1. So on and so forth is possible. We will see in the next lecture how to get higher order multiplexers using lower order multiplexers.